Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to do part 2 of differential operators and annihilation. So I'm going to use the methods that we did in that previous video to be able to solve a differential equation. And let's start out with this. So the whole goal of this is that we can solve differential equations that are non-homogeneous, that are not equal to 0 on the right-hand side. So I got a second order linear, non-homogeneous differential equation, and I'm going to solve this through annihilation. So let's start out with the differential operators on this left-hand side. So I can say that this is d2 plus 3d plus 2 y is equal to this 4x squared. So this is just a re-representation of second derivative of y, 3 times the first derivative of y, then plus 2y. Now my goal is to really kind of turn this into a homogeneous differential equation, so I want to annihilate this 4x squared. So the question is, what do I have to, what differential operator annihilates that? So if I take the differential operator of 1 power bigger than that 4x squared, we know that the third derivative of something x squared is going to be equal to 0. So what I do to the left, right, I'm going to have to also do to the left. So this is going to be of, this thing. So this is d2 plus 3d plus 2. Now again, this right-hand side is equal to 0. So then I'm going to have my d cubed, d squared plus 3d plus 2y. And what I can do is I can factor this thing completely. So I'm going to get a d cubed. This is going to be a d plus 3. This is going to be a d plus 1. Y is equal to 0. Now, very similar to the characteristic equation, the zeros of these things are going to be related to your solutions. So let's say the zeros would be, r1 would be equal to 0. R2 would also be equal to 0, and R3 would also be equal to 0 because that's what makes this thing 0. So I have repeated roots of 0, 3 of them. And then what makes this 0 is going to be a negative 3. So R4 is going to be negative 3. And then our R5 is going to be equal to negative 1. So when I write this, my solution, y, is going to be equal to, well, this is c1e to the 0x plus c2e to the, this is a repeated root. So I already have a e to the 0x. I'm going to have to do an xe to the 0x. And again, I'd have another e to the 0x from here. Since it's repeated, I'm going to have to increase the power on this. So this is going to be c3x squared e to the 0x. And that's going to take care of that linear dependency. And then finally, for these pieces, I'm going to have a c4 e to the minus 3x plus a c5 e to the minus 1x. Now, some part of this actually is the particular, and some part of it's the complementary solution. So the complementary of it, when it's equal to 0, if it was homogeneous, if this was homogeneous, then really the roots of this d plus 3 and d minus 1, this negative 3 and negative 1 would be that solution. And the particular solution is going to come from the non-homogeneous part. So we can say really the complementary solution being, this part of it. So c4e to the minus 3x plus c5e to the minus x. And if you want to find those solutions, you'd have to have some kind of if you want to find the coefficients, you're going to have some initial conditions. But then our particular solution is going to come from, this part. We can see that it's this piece. Now, any e to the 0x is just going to be, c1. c2x e to the 0x is just 1, plus a c3 x squared e to the 0x is going to be equal to 1. So we can really tell that from like a previous lecture under Professor Goins that if that the particular solution has to come from the family of quadratics, and this really just kind of verifies that family of quadratics through annihilation. So this is really just proof that this works. So if you do want to find the coefficients c1, c2, and c3, well, we know that in order to do that, I'm going to have to find its derivative. So prime is going to be equal to c2 plus 2c3x. And then its second derivative is going to be the derivative of this. So this is going to be plus equal positive 2c3. And if I want to find the coefficients, C1, C2, and C3, they have to work for this. So let's just go ahead and find those coefficients. So y double prime, so plug it into here. This is going to be 2. Let's make sure I have enough room. So this is 2C3 plus 3 times the first derivative, which is going to be here. So this is C2 plus 2C3. And then finally plus 2 times the original, oh, there should be an x here, plus the original solution, which is going to be a C1 plus C2x plus C3x squared. And this is supposed to be equal to, this 4x squared. So what we're going to do is we're going to expand this, and through a system of equations, we'll find C1, C2, and C3. So expanding, I have 2C3 plus 3C2 plus 6C3x plus, this is supposed to be multiplied by 2y. So this is going to be a 2C1 plus 2C2 plus 2C3, C2x plus 2C3x squared. And this is going to be equal to a 4x squared. Now let's reorder these. I want to know what my constants are. So constants, I have a 2C3 plus 3C2, and finally plus this 2C1. Now the coefficients in front of x are going to be a 6C3 and also plus a 2C2, and that's going to be for your x. And then the constants in front of x squared really comes only from this particular term, so 2C3x squared, and this has to be equal to 4x squared. Well, remember that this is going to be, this would be 0 plus 0x plus 4x squared. So if you were, if you want to figure out their solutions, you have to match their coefficients, which means, this has to be equal to 0, this 2 has to be equal to 0, and this part has to be equal to 4, which guarantees that, if 2C3 is equal to 4, then C3 is equal to 2. So at least we have one of them. Now again, this is supposed to be equal to 0. Well, C3 is, this is supposed to be equal to 0. So 2 times 2 plus 3C2 plus 2C1 has to be equal to 0. And then similarly, this thing has to be equal to 0. So 6 times 2 plus 2C2 has to be equal to 0 because, again, they have to match those coefficients. So this is this one I can solve. So this is 12 plus 2C2 is equal to 0. So 2C2 is equal to minus 12. So C2 is negative 6. And now I know everything besides C1 now. So this is going to be 4 plus 3 times negative 6 plus 2C1 is equal to 0. So 4 minus 18, so minus 14 plus 2C1 is equal to 0, so 2C1 is equal to 14, so C1 is equal to 7. So really this guarantees that our particular solution, yp, is going to be equal to, well, C1 was 7, plus C2, which is negative 6x, so minus 6x, and then C3 is going to be plus a 2x squared. So that's what we can write for our general solution. Without knowing some initial conditions to be able to find these two things, I can say that this is, we'll say C4, but you can name it C1 and C2 again if you want to. So C4 e to the minus 3x plus C5 e to the minus x plus our 7 minus 6x plus 2x squared. And that right there is our general solution. So what I'm going to do for the next example is I'm not going to go through and find the coefficients. I really just want to kind of verify that the particular solution is kind of what's expected using, from like the previous lecture, using differential operators and annihilation. All right, so if I want to find the differential operators that annihilate these things, first I'm going to work with this left-hand side to, kind of work out the, your complementary solution before I use this to find your particular solution. So this is, D2, and that is a minus 3D, that's right, minus 3D, and this is going to be equal to y. So this is the second derivative, minus 3 times the first derivative. And then over here, really I have two different families. I have this family that I'm going to have to annihilate, and we know that that is done through. Well, let's just kind of look at each piece over here. So what if I have my 8 e to the 3x? You know, what differential operator annihilates that? And what we know is this is going to be a d minus 3 to the first power. And the reason why it's to the first power, because really this is d minus 3 to the 1, because this is an 8x to the 0 e to the 3x. So this power here has to be 1 more than this power on x. And since this doesn't have an x, that means that power had to be equal to 0. And then if I want to annihilate the sine function, well, this is actually a special case. If I have 4e to the 0x sine x as well, what we know is that the differential operator that annihilates this thing is going to be that bigger one. We have that that d squared minus alpha d, my bad, plus we have alpha squared plus beta squared. So we have to figure out, what is our alpha and then what is our beta. So this is a special case of something that looks like a e to the 0x sine beta x. And if I was going to annihilate this thing, what we know in order to use that is it's going to be equal to, we have this d squared minus 2 alpha d plus alpha squared plus beta squared, all to the nth power. Now, actually, this is a special case as well because there really is an x to the 0 here as well. So let's start out with this nth power. Well, since x is equal to 0, this nth power is just going to be equal to 1. Now, your alpha is going to be the coefficient in front of the exponential power, so that means alpha is also equal to 0, so this is going to be equal to 0. So d squared minus 2 times 0d plus we have 0 squared. But we know beta in this case is going to be equal to 1 in our case, so this is going to be plus our beta times, the sine of bx essentially. So if I have, your 4 sine of just 1x, then what's going to annihilate this is this power is kind of redundant. Let's just do it this way. So this is going to be d squared plus 4. And really this 4 doesn't matter because it's a constant, so you can pull that thing out. And if this annihilates this, then this will be equal to 0, and 4 times 0 will be equal to 0. So I'm really not using that 4 to find any of the alpha and betas. Okay, so let's work on that. What I know is that I'm going to need to annihilate, this thing. So what's going to do that is this is just going to be a d minus 3. That's going to annihilate this piece, and then I also am going to have to do this d squared plus 4. And that's going to annihilate this piece, so this is going to be times this 8e to the 3x plus 4 sine of x. Not 4, 1, you silly. Not 4, but 1. 1, thank you. 1 because of that one. Okay, so what we know is that I can factor this thing completely. So this is going to be, this, is going to be d plus I times d minus I, or if you want to set it equal to 0 and then prove that you get plus or minus I, this is going to be a d minus 3, and this is going to be a d, and then I have a d minus 3, and then this entire side is going to be equal to 0. So this is going to give us some R value. So let's start with the real ones. We have 0, and then we have 2 factors of 3. So I have R1 is going to be equal to 0, R2 is going to be equal to 3, R3 is also going to be equal to 3, and then we also have some complex roots, so I'm going to have an I from this, and then also a minus I from this. So that means that our differential equation is going to look like this. We're going to have y is equal to, let's see, c1 e to the 0x, that comes from this, plus we're going to have a c2 e to the 3x, which comes from this. It's a repeated root, so I'm going to have a c3x e to the 3x, so you introduce that extra x. And then for the complex roots, we know that these things have to do with trig functions, so this is going to be plus e to the 0x, and the reason why is, let's just kind of investigate this. The way we did it before, I'm going to use, we usually use alpha and beta, but we use alpha plus beta I. So this is, you know, the solution is e to the alpha x times the cosine of beta x plus the sine of beta x. So, you know, if you have complex roots, you plus or minus this thing, you're going to get these two things. So really this is 0 plus I, this is 0 minus I, really guaranteeing that this is e to the 0x. And then we have sine or cosine first. It doesn't really matter. So let's say the sine first. So the sine of, well, the coefficient beta is going to be equal to 1. The plus or minus is right here. So this is just going to be a 1x plus the cosine of 1x. Now, we can separate this into our complementary and our particular. You know that our complementary came from this piece here, which is here. And then our particular actually comes from, you know, these remaining roots. So y sub c is going to come from c1e to the 0x, which I should just say c1. We'll fix that in a second here. So c1 plus our 3, which is going to be plus our c2e to the 3x. And then our particular solution is going to come from the remaining part, so it's going to come from this, our c3x e to the 3x, plus e to the 0 is just going to be equal to 1, so this is going to be plus, oh, I forgot to put a coefficient in front of there, so this is going to be c4, so c4, my bad, the coefficients are supposed to go here. So this should be a C1, and this should be a, well, a C4, and this should be a C5. So C4 sine x plus C5 cosine of x. Now again, you can find these coefficients by taking, you know, its first derivative, its second derivative, plug it in here, and then go ahead and find those things. And if you do want to work, what you're going to get, well, I'll actually let you do that. I think that's better off for you. So this really is just trying to verify that we get kind of what we expect. Let's just double check that this makes sense. So we know that if I was going to find the complementary solution, it's clear. It comes from the, you know, the roots of this characteristic equation, which is clearly going to be for this thing. Now you know that this function is going to definitely have an e to the 3x, but since the complementary already has an e to the 3x, you're going to have to introduce an x, which is why you got the x e to the 3x. And you also have to work with the family of sines and cosines, because I have that 4 sine of x. So, you know, for every sine, when you take its derivative, you're going to get a cosine. So the family of 4 sine of x is actually, you know, some constant sine of x plus some constant cosine of x, and that's what we have here. So really, this is just kind of verifying what we did in like the previous video of why this is obtained, you know, and this is done through annihilators. So if you like the videos, please subscribe.